our channel Knowledge of. Friends, subscribe to our channel and click the bell icon for the latest update. Today we're gonna start with your chemistry class, that is of class 12th, and this is your class 10. And as you know that we had done your class 9 here, and this is your unit, which is your unit 4, that is your chemical kinetics. This is the first class of chemical kinetics. Before that we had completed the 3 unit, which is unit 1 is your the solid state, the second unit which we have is your the solution, and the third which we have done is your electrochemistry, and that is of the last classes, till 9 classes we had done that. And now in this unit 4 we will start in the 10th class, and that is your chemical kinetics. Before starting with this, first of all you have to know that what is chemical kinetics and what role it performs. Before starting with this, it's a huge request from my side to all the viewers to please go through with the subscribe button, and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. In terms of chemical kinetics here, that the chemical kinetics is the branch of chemistry which deals with the study of the speeds or the rate of the chemical reaction, the factor affecting the rates of the reactions, and the mechanism by which the reaction proceeds is known as chemical kinetics here. In terms of chemistry, we talk about it, like chemical kinetics help us to understand how chemical reaction occurs, and in chemistry by its very nature is concerned that with the change and substance when well-defined properties are converted by chemical reactions into other substance with different properties. For any chemical reaction, the chemists try to find out. The first, they find it out by the feasibility of the chemical reaction, which can be predicted by the thermodynamics. As you know that the reactions of delta G, that is less than 0 at a constant temperature, and the pressure is feasible here. The second thing that they chemists try to find out the extent to which a reaction will proceed, that can be determined from chemical equilibrium. And the other is that the speed of the reaction, that is the time taken by the reaction to reach equilibrium as well, that they had to find it out as well. So for that, along with the feasibility and extent, it is equally important to know the rate of the factor controlling the rate of the chemical reaction for its complete understanding. For example, which parameter determine as how rapidly food gets spoiled, and how to design a rapidly setting material for the dental filling, or what control the rate at which the fuse burns, or in an auto engine. All these questions that can be answered by the branch of chemistry which deals with the study of reaction rates and their mechanism, that called chemical kinetics, even though which we had discussed here. The word kinetics is derived from the Greek word which is kinesis, that means the movement, and thermodynamics tells about the feasibility of the reaction, whereas that chemical kinetic tells us about the rate of the reaction here. For example, thermodynamic, but in that is the thermodynamic data, in reality the conversion rate is so slow that the change is not perceptible at all, and therefore most people think that the diamond is forever. Kinetics studies not only help to determine the speed or the rate of the chemical reaction, but also describe the condition by which the reaction rate can be altered, and that is the factors we talk about, that the factors such as concentration, temperature, pressure and catalyst effects as well that affect the rate of the reaction. At the macroscopic level, we are interested to the amount reacted or formed, and the rates of their consumptions, amount reacted or formed, and the rate of their consumption formation as well. And at the molecular level, the reaction mechanism involve orientation and energy of molecules undergoing the collisions that are discussed. So in this unit, we shall be dealing with the average and instantaneous rate of reaction, and the factor affecting these some elements, ideas that are about the collision of the reaction rates that are also given. However, in order to understand all these, let us first learn about the reaction rate here. So first we'll go ahead with the reaction rate here, that is also an important one. So the first we'll discuss about, which is rate of chemical reaction. So rate of chemical reaction here. Here are some reactions such as ionic reaction that occurs very fast. For example, the precipitation of silver chloride that occur instantaneous by mixing an aqueous solutions of silver nitrate and sodium chloride. On the other hand, some reactions are very slow. For example, rusting of iron in the presence of air and moisture. And also there are the reactions like the inversions of cane sugar and hydrolysis of starch, which proceed with the moderate speed. And can you think of more examples from each category? You must be knowing that the speed of an automobile is expressed in the terms of change in the position or the distance covered by it in a certain period of time. Similarly, the speed of reactions or the rate of the reaction that can be defined as a change in concentration of a reaction or a product in unit time. That to be more specific, it can be expressed in the terms of, like the first we have that the rate decrease in concentration of any of one of the reactants here, and the second we have here in reference towards it, that is on the case that the rate of react increases in concentration of any one of the product as well. So we can say that you have to consider the hypothetically reaction assuming that the volume of the system remains constant, where R tends to P, you can say that. And on the same cases we will be going ahead to solve it out as well. So for that sake, it will be R tends to P, as I told you. So here 1 mole of the reactant R product produces 1 mole of the product with that is P, and that is R1 and P1, that concentrations of RP respectively at R2 and P2, and their concentration at a time T2, so that we can represent that as in the form of delta T equals to T2 minus T1 delta R R2 minus R1, and that is delta P equals to P2 minus P1 here. So the square brackets of these expressions are to be expressed as molar concentration and rate of disappearance of R, that we'll talk about it, and that you have to even find it out as well. So yes, rate of disappearance of R equals to decrease in concentration of R upon time taken, which is equals to minus delta of R whole upon delta T here. On the same cases where the rate of appearance of P, will talk about it, that we have to go ahead, and on the same cases that is also an important one here. So on the same cases that we have to represent it, and that is the rate of appearance of P is equals to increase in concentration of P upon time taken, which is equals to plus of delta P whole upon delta T, and that is since here that is delta of R is negative quantity, and as the concentration of the reactant is decreasing, so it is multiplied with n here, and to make the rate of the reaction positive quantity as well. So here that is the given represent the average rate of a reaction, and that will represent it. So here we go ahead further, that we have to discuss about it, and in the same cases that the average rate depends upon the change in concentration of the reactants or the product, and the time taken for that the change that to be occur as well. On the same cases, we'll talk about it where the instantaneous and average rate of the reaction being take place in reference towards time. So when it is the instantaneous, so that will be go into the sliding form like this, and when it is coming towards top to decreasing order, and then we will talk about the average rate of the reaction. It will come from from down to up, that it goes here, and where in the first respective that the concentration of reactant versus the time, where the slope is negative here. The one, and that will talk about the unit of the rate of the reaction as well. Unit of rate of reaction. So in the same cases here, for that, from this equation it is clear that the units of the rate of the are concentration time. For example, if the concentration is in the mole liter inverse and the time in the second, that the unit will be the mole liter inverse and second inverse. So however, in the gaseous reactions, when the concentration of the gaseous is expressed in terms of their that is the partial pressure, so then the units of the rate of the reactions, that is equals, the equation will be the ATM second inverse as well, that we talk about it. And now we will be solving it out, the first question of the sessions of this chemical kinetics, and that is also even though important. The question is from the concentration of C4H9Cl, which is butyl chloride, at the different times that given below. So calculate the average rate of the reactions here. The reaction we have here, C4H9Cl plus H2O, it will give C4H9OH plus HCl. So during the different intervals of time, like time we have is your 0, T, 50, 100, 150 and 200, 300, 400, 700 and 800 respectively, and that's the concentration we have a different here. So we can determine the difference in the concentrations of the different, that will find it out, and even though that we have to go ahead as well, and which is also an important one here. So yes, we'll go ahead and we'll find out the solution for those, and yes, of course, that will represent it here as well. So for that, we'll be going ahead. The question we have here, as I told you, so just I write it down for you all, so that you will be into, you can just copy it down and you can just solve it out as well. So question number 1 of the sessions as well, from the concentrations of C4H9Cl, which is butyl chloride, at different times given below. Calculate the average rate that we have. So calculate the average rate of the reaction. Then we have a reaction here, C4H9Cl plus H2O give C4H9OH plus HCl. So during a different interval of time, time interval we have C4H9Cl mole liter inverse that we have. So here is the value we have 0, 50, 100, 150, 200, 300, 400, 700, and yes, of course, 800. And now for that, the value that we are representing here. For 0 time that we have is 0.100. For the 50 we have 0.0905. For 100 0.0820. 150 0.0741. 200 0.067. And for 300 we have 0.0549. 400 0.0439. 700 0.0210. And for 800 0.017 here. On the same cases we can determine just for the solution that we talk about it, as you can see the question here as follows. And on the same cases here we can determine the difference in concentrations over the different intervals of the time, and thus determine the average rate by dividing the delta R and by delta T, which is you know very well the formula, the delta R upon delta T, which is R2 minus R1 and minus T2 minus T1, that we will implement here, and we will be finding it out the solution for this as well. So on the same cases, yes, we will be drawing sort of a table here for the average rate of hydrolysis of the butyl chloride, and yes, we then will find it out as well. So yes, we'll go ahead. So first we'll represent it that in the form of, which is C4H9 Cl. This is for the T1, and which is your mole liter inverse. Another we have C4H9 Cl. This is for T2 upon mole liter inverse. This is T1 by S. This is T2 by S. We'll find out. And then another we have is your R average into 10 to the power 4 mole liter inverse second inverse is equals to C4H9Cl, that is your T2, minus C4H9Cl, that is T1, and that T2 minus T1 here, and that is multiplied by it. So let's find it out for this, and we'll put the value for that as well. We'll just represent the value first, that is we have is 0.100, 0.0905, 0.0820, 0.0741, 0.0671, 0.0549, 0.0439, and then another we have here is your 4939, then 0.0210, that we have a value here. So we'll just make a margin here so that it will be differentiated, that what we have to represent it here. Okay, for that we have to find out. Yes, we'll represent the value for these all, and that is also an important one here. For 0.100 here, that will represent it, which is 0.0905. For T1 by S, that we have their value is 0. For this is 50, and this is your 1.90. We'll implement and the value, and then we'll solve it out as well. The another we have is 0.0820. This is 50, 100, and this is your 1.70. Another we have 0.0741, 100, 150, and this is 1.58. 0.0671, this is 150, 200, and this is your 1.40. 0.0549, this is 200, this is 300, and this is 1.22. The another we have 0.0439, 300, and that is your 400, and that is your 1.10. 0.0335, 400, 500, and 1.04. The another we have is 0.017. This is 700 and this is 800, and that is your 0.4 that it is represented here as well. So on the same cases that it can be seen here that the average rate falls from 1.90 into 0 power minus 4 mole liter inverse to 0. That is we have here the value that is been representing is 0.4 into 10 to the power minus 4 mole liter inverse second inverse. So however, average rate cannot be used to predict the rate of the reaction at a particular instant, as it would be the constant time interval for which it is calculated. So to express the rate of a particular moment of time, we determine the instantaneous rate, and it is obtained. We consider the average rate of the smallest time interval, say dt, and the delta t approaches to 0, and hence mathematically for the infinite that is your infinite similarly of the dt instantaneous rate is given by, and that will represent it, and which is in the form of which we have as follows, like will represented that as well in the form of r average equals to minus delta of r whole upon delta t equals to delta p whole upon delta t, as delta t equals to tends to 0, so we can say that r average that will be representing here. So on the same cases we'll represent it that in the form of like r instant equals to minus d of r whole upon dt, which is equals to d of p whole upon dt here as well. On the same cases for that, it can be determined graphically by drawing a tangent at time t on either of the curves here, and that is for the concentrations of r and p, and versus that is of time here, and on the same cases that and calculating that its slopes as well. And in this problem here, r instant at 600 seconds, for example, that can be calculated by plotting concentrations of butyl chloride as a functions of the time, and the tangent is drawn for the touches the curve at t equals to 600 seconds. The slope of the tangent that gives the instantaneous rate here, and that we have to even talk about it, which is your that will be r as follows, and that is r instant at 600 seconds equals to minus 0.0165 minus 0.037 whole upon 800 minus 400 mole liter inverse equals to 5.12 into 10 to the power minus 5 mole liter inverse second inverse at t equals to 250 seconds. R instant equals to 1.22 into 10 to the power minus 4 mole liter inverse second inverse at t equals to 350 seconds. R instant equals to 1.0 into 10 to the power minus 4 mole liter inverse second inverse, t equals to 450 seconds. R instant equals to 6.4 into 10 to the power minus 5 mole liter inverse second inverse. And now we considered a reaction here, which is the reaction we will be following having is your in the form of Hg plus Cl2 will give you HgCl2 gas, which is in the form of, and where the stoichiometric coefficients of the reactant and the product that are same, and then the rate of the reaction that to be given is in the form of the reaction will have, there is a rate of reaction equals to Hg upon delta T equals to minus Cl2 whole upon delta T, which is equals to delta, that is your Hg, that we have is your HgCl2 whole upon delta T here, that it represented here in the form. So now that is the rate of the disappearance of any reaction is as same as the rate of appearance of the product, but in the following reaction the 2 moles of the HI decomposes to produce the 1 mole of each of H2 and I2. So that will the reaction that will represented here in the form, and that we have is your 2HI that will give in the form of gases, that is in the form. So that is in the form of 2HI that will give H2 gases plus I2 here. In the form of the gases here, and on the same cases we'll go ahead further, which is for expressing the rate of the such reactions where the stoichiometric coefficients of the reactions or product are not equals to 1, and the rate of the disappearance of any of the reactants or the rate of the appearance of the product is divided by their respective stoichiometric coefficient. Since the rate of the consumptions of HI is twice that the rate of the formations of H2 or I2, and to make them equal, the term that is the delta change in HI is divided by 2. The rate of the reaction is given to be in the form of like rate of reaction equals to minus 1 by 2 delta of HI whole upon delta T equals to delta H2 whole upon delta T equals to delta of I2 equals to delta T. So similarly for the reaction here, that we have another reaction which is 5Br, and that is your 5Br which is in the form of aqueous minus that will be 5 plus BrO3 aqueous plus 6H plus aqueous, that gives 3Br2 aqueous, and that we have plus 3H2O, that is liquid. So that is the rate for that. We'll find out for that. The rate is equals to minus 1 by 5 delta of Br whole upon that is your delta T equals to minus delta BrO3 delta T equals to minus 1 by 6 delta H plus whole upon delta T equals to 1 by 3 delta Br2 whole upon delta T equals to 1 by 3 delta H2O upon delta T. For gaseous reactions at a constant temperature, there the concentration is directly proportional and to the partial pressures of the species, and hence the rate of that can be expressed here as the rate of the reaction in a partial pressure of the reactant, and or as we can say that, or the product as well. And on the same cases we'll be going ahead with another one, and that we will discuss the another question here, which is that the decomposition of N2O5 in CCl4 at 318 Kelvin has been studied by the monitoring the concentrations of N2O5 in the solution, and initially that the concentration of N2O5 is 2.33 mole-liter inverse, and after 184 minutes it reduces to 2.08 mole-liter inverse. So that reactions takes place according to the equation which we have is your 2N2O5 in the form of gases will give 2NO2 gases plus O2 gases as well. On the same cases, you have to calculate the average rate of the reaction in the terms of the hours, minutes and second. What is the rate of the productions of NO2 during this period as well, that you have to find out. Now we'll go ahead further and we'll discuss about it, and which is also very important, as I told you before as well, and even though right now, even though I am telling you about it, because these were the things that is important, and these were the questions is also important that you have to consider about it. Let's go ahead for the question of the session. This is the question second of the session here of this unit 4. The question is the decomposition of N2O5 in CCl4 at 318 Kelvin has been studied by monitoring the concentration of N2O5 in the solution initially. The concentration of N2O5 is 2.33 mole liter inverse, and after 184 minutes it is reduced to 2.08 mole liter inverse. The reaction takes place according to the equation we have as follows. For the solution for the equation we have, first we'll discuss about it, which is 2N2O5 in the form of gases will give 4NO2 gases plus O2 gases here. So we have to calculate the average rate of this reaction in terms of hour, minute, second. What is the rate of production of Na2 during this period? So now, yes, we'll have a solution for this as well. We'll talk about it. Average rate equals to 1/2 minus delta N2O5 upon delta T is equals to minus 1/2, that we have 2.08 minus 2.33 mole liter inverse whole upon 184 minutes. Further it will be 6.79 into 10 to the power minus 4 mole liter inverse per minute equals to 6.79 into 10 to the power minus 4 mole liter inverse minute inverse into 100 minute, sorry, into 60 minute per hour, 60 minute per hour. Then we will convert it, we'll get 4.07 into 10 to the power minus 2 mole liter inverse per hour equals to 6.79 into 10 to the power minus 4 mole liter inverse, and per minute here, which is equals to 1.13 into 10 to the power minus 5 mole liter inverse second tan inverse. So it may be resemble that. So it may be resemble that here, that is the rate equals to 1 upon 4 delta NO2 whole upon delta T, which is NO2 upon delta T equals to 6.79 into 10 to the power minus 4 into 4 mole. Liter inverse minute inverse equals to 2.72 into 10 to the power minus 3 mole liter inverse and minute inverse that we have as an answer here. Now we'll discuss more of the question. I will give you as a homework that you have to solve it out. That is, for the reaction R tends to P, the concentration of the reactant changes from 0.03 mole to 0.02 mole in 25 minutes. You have to calculate the rate of the reaction using the unit of time, both in minute and second, that as I told you, and we had done this one as well in the above here. This one you have to solve like that only. Then another question is, in the reaction to A that tends to the product, so then the concentration of A decreases from that 0.5 mole liter inverse to 0.4 mole liter inverse in 10 minutes. So you have to calculate the rate during this interval as well. Now we'll go ahead to discuss about another topic that we have to discuss, which is the factor influencing the rate of the reactions here, and that we have to go ahead. So we'll go ahead. Factors influencing rate of reaction. So factors influencing the rate of reactions here, where the rate of the reaction that depends upon the experimental condition as concentrations of reactant, which is pressure in the cases of the gases, temperatures and catalysts. And for that, the first we'll talk about it, which is your that is the dependence on of a rate of concentration. Dependence of rate on concentration. So in this, if I'm going ahead, where the rate of the chemical reaction at a given temperature that may depend on the concentration of one or more reactants and product. The representation of the rate of the reaction in terms of concentrations of the reactant is known as rate law, and it is also called the rate equations, or that is the rate expressions as well. We'll go ahead further, we'll discuss about it, which is the second one. We'll talk about that is the second one, is your rate expression and rate constant. Rate expression and rate constant here, that is the results that clearly that the rate of the reaction decreases the passage of time as the concentration of the reactant decreases, and where the conversely the rates generally increase when the reactant concentration increases. So a reaction depends upon the concentration of the reactant, where we can say that rate is directly proportional to the concentration of reactant as well. We'll consider a general reaction here, that to be we have to consider about it, and even though which we have to go ahead further, and the same basis that we have the general equation we have here, that is your 2a plus b, that is small a, okay, a and then b and b, that tends to c and c plus d and d here. So here this is the small a, b, c, d. They are the stoichiometric coefficients of the reactant and product, and the rate of the expressions for this reaction will just write it down like rate equals to, rate is directly proportional to a of x and b of y, where that x and y may or may not be equals to the stoichiometric coefficient a and b of the reactants in the above equation, that can be written in the form of rate equals to k alpha equal approximate sign directly proportional हटेगा तो constant आता है, so that is a k constant here, which is a of x and b of y that we have. So here this form of the equation is known as a differential rate equation, where k is a proportionality constant that is called as rate constant. So the equation here that which relates the rate of the reaction to the concentration of the reaction is called the rate law or the rate expression. Thus, the rate law is the expressions in which the reactions rate is given in terms of molar concentration of reactions with each term raised to some power, and which may or may not be the same as the stoichiometric coefficient of the reacting species in the balanced chemical equation. For example, for that we will represent 2NO, that is in the form of gas, plus O2 in the form of gas will give 2NO2 gas here. That is, in this we can measure the rate of the reactions as the functions of initial concentration, either by keeping the concentrations of one of the reactant constant and changing the concentration of the other reactant, or by changing the concentration of the both the reactant. The following result will be obtained here, and that we even have to find out here. On the same cases, we will be having a table here for that, that is the initial rate for the formations of NO2, and where we have to make a sort of a table, and let's go ahead to make it at our visible. That's your experiment. And then we have initial NO per mole liter inverse, then initial mole liter inverse, and initial state of formations of NO2 and mole liter inverse here. This is 1, 2, 3 and 4. For 1 it is 0.30, 0.60, 0.30, then 0.60. For 0.30 for the initial year, that is 0.30 itself, and this is your B that we have is 0.096. This is for 0.60 we have 0.30, that is 0.384, 0.60 it is 0.192, and 0.60 again, then we have 0.768. It is obvious that after looking at a result that when the concentrations of NO is doubled and that of O2 is kept constant, then the initial rate increases by the factor of 4 form from 0.096 to 0.384 mole liter inverse. This indicates that the rate of the reactions upon the squares of the concentrations of NO, and when concentrations of NO is kept constant and the concentrations of the O2 is doubled, the rate also gets doubled, indicating that rate depends on the concentrations of O2 to the first power, and hence the rate equations for this reaction will be in the form of like rate equals to K NO and O2 here. On the same cases, where we go ahead further on the behalf of it, that the differential form of this rate of the expression, that is which can be represented in the form here, and that is your V of R whole upon dt minus equals to K NO2 and O2. So now we observe that for the reaction of the rate of the equation, that the form of the experimental data, that exponents of the concentration that are same as the stoichiometric coefficients in the balanced chemical equation. Some other examples are to be given as like reactions and the experimental rate that we have. So that is the reactions. First we will be having here is your CHCl3 plus Cl2, that gives CCl4 plus HCl. And the rate reaction, the experimental rate expressions we have. So rate equals to K CHCl3 by Cl2 half, and the other we have here, that is the second equation we have, which is C2H5 plus H2O will give CH3COOH plus C2H5OH. The rate expression we have for that as well, that is K CH3COOC2 H5OH, that we will find it out here. The same cases in these reactions, that the exponents of the concentration terms that are as same as the stoichiometric coefficient, and thus we can say that the rate law for any reaction that cannot be predicted by the merely looking at the balanced chemical equation theoretically, but that is that must determine experimentally as well. Now we'll go ahead further. We'll discuss about the another one, and which is your the order of reaction here. That is the third topic under it. Order of reaction. So in terms of order of reaction, in the rate of the reaction, where the rate is equals to, as I told you, and which is in the form of rate equals to K A of x and T of y. So here x and y indicates how sensitive the rate is to be changed in the concentrations of A and B. And some of these exponent is like x plus y, that gives the order of the reaction, where x and y represents the order with respect to the reactant A and B respectively. Hence the sum of the powers of the concentrations of the reactants in the rate law expression is called the order of that chemical reaction. An order of the reaction that can be 0, 1, 2, 3, even a fraction as well. An order of reaction means the rate of the reaction independent concentrations of the reactions as well. On the same cases, now we'll do a one sort of a question here that that is also an important one, and yes, we'll do that. This is the third question of the sessions. So here, to calculate the overall order of the reactions which have the rate of expressions that we have. So yes, for that as well, calculate the overall order of a reaction which has rate expression. So with the same cases here, and on the same behalf we have to go ahead for the expressions, and that the first we have a part, and that is your rate equals to K A 1 by 2 B 3 by 2 here. So for that we'll solve it out here for the solution for this. The rate equals to K A x B y. So which is order is x plus y. So order will get is 1 by 2 plus 3 by 2. We'll take as an LCM 2. The 3 plus 1 4 by 2. So 2 1 the 2 2 the 4. So that is your answer will be 2. So here the second order we have for the another question, the second part of this particular question here. That is another one, and which is in the form of, that is the AF equation. We have rate equals to K A of A 3 by 2 and B minus 1. So order we have 3 by 2 plus minus 1 equals to 1 by 2. So here the half order we have. Now a balanced chemical equation that never gives up as a true picture of that is how a reaction takes place, since rarely a reaction gets completed in any step. So the reaction taking place in one step that are called the elementary reaction, and the sequence of the elementary reactions is called like that is your mechanism that gives us a product, and the reactions are called complex reactions as well. On the same cases, yes, we'll go ahead further, which is in the form that these may be the consecutive reactions, like example your oxidation of ethane of the CO2 to CO2 and H2O passes through a series of intermediate steps in which the alcohol, aldehyde and acids are formed. Reverse reactions are, and side reaction, that is nitrations of phenol yields O-nitrophenol and a P-nitrophenol as well. Now we'll go ahead, we'll continue with the next coming class. First of all, it's a huge request from my side to all the viewers to please go through with the subscribe button, and please like, share and subscribe to the channel, so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. In terms of if I'm talking about the chemistry of class 12, other than that, we are dealing with we had near about to complete software engineering, where we had completed unit 1, unit 2, unit 3 and unit 4 here as well. And we, in unit 5 we have to cover up the questions of the questions that has been asked in a different examination paper of different year of examination paper of BTech, that will deal with it in the next coming class. And after that, quantitative aptitude we are dealing with, and that we had started with arithmetical ability, where we had completed the operations on number, LCM and SCF of numbers, and that is the another we have done your decimal fraction and simplification that we are dealing with. And we are, even though we had reached more than 250 question as well. After that, we are dealing with the reasoning. As I told you, that reasoning has been divided into two parts: verbal reasoning and non-verbal reasoning. In the verbal reasoning, we had completed the general mental ability and the logic reasoning, and in the non-verbal reasoning, we had completed more than 1,000 questions of series, analogy and classification, analytical reasoning, mirror image, and next in the next coming class, we'll have to start with the water image as well. After that, talking about the chemistry here, that of the class 12, that we are dealing with the part 1 of the NCERT here, where we had completed unit 1, which that the solid state, we had covered up the general characteristic of solid state, amorphous and crystalline solid, classification of crystalline solid, crystal lattice and unit cell, number of atoms in the unit cell, closed packed structures, packing efficiency, calculation involving the unit cell dimensions, imperfections in solid, electrical properties, magnetic properties as well. Another we have to cover up this, that is the unit 2, which is solution, the type of solution, expressing the concentration of solution, solubility, vapor pressures of liquid solution, ideal and non-ideal solution, correlative property and determination of the molar masses, abnormal molar masses as well. The next third unit, we have to start with the electrochemistry. We had completed that, electrochemical cells, galvanic cells, Nernst equation, conductance of electrolytic cells, the solutions, electrolytic cells and electrolysers, batteries, fuel cells, and of course the corrosion here. In unit 4, which we had, even though started, as you can see that we had started with chemical kinetics, here we had completed the rate of the reactions, factors influencing the rate of the reaction that we are dealing with, and we had covered up the third one here. So fourth we will discuss in the next coming classes. Then we'll discuss integrated reactions, rate of reactions, pseudo first order reaction, temperature dependence of the rate of the reaction, collision theory of the chemical reaction as well. After that, unit 5th we have to cover up, and in the unit 5th we have to discuss the adsorption, catalyst, colloids, classification of colloids, emulsions and colloids around us. Unit 6 is general principle and processes of isolations of element, which is occurrence of metal, concentration of ores, extractions of fluid oil from the concentrated ore, thermodynamic principle of metallurgy, electrochemical principle of metallurgy, oxidation, reduction, refining, uses of aluminium, copper, zinc and iron. The P block element, we have to discuss the group 15 element, dinitrogen, ammonium, oxides of nitrogen, nitric acid, phosphorus, allotropic forms, first sign, phosphorus halides, also acids of phosphorus as well. Group 16 element, that is dinitrogen, simple oxides, ozones, that we have to discuss here. And on the same cases, we have to discuss the sulfur allotropic forms as well, and sulfur dioxide, also that is acids of sulfur, sulfuric acid. Group 17 element, chlorine, hydrogen chloride, also acids of halogens, interhalogens compound, group 18 element as well. After that, we will discuss unit 8, which is unit that is the D and F block element, which is positions in the periodic table, extra electronic configuration of the D block element, general properties of transition element D block, some important compounds of transition element, the lanthanides, actinides, some application of D and F block element as well. We'll talk about the coordination compound, which is the Werner series of the coordination compound, definition of some important terms pertaining to the coordination compound as well, nomenclature of the coordination compound, isomerism of the coordination compound, bonding in the coordination compound, bonds in the metal carbonalysis, stability of the coordination compound, importance of the application of the coordination compound as well. After that, we'll discuss many more things in the next second part of the chemistry as well. So first of all, it's a huge request from my side to all the viewers to please go through with the subscribe button, and please like, share and subscribe our channel, so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. And thank you, hope you enjoyed this video. If you like this video, please give a thumbs up and give a suggestion in the comment box, and please support us as you had supported till the end. Thank you.